We've used the product rule to calculate some derivatives. We've even seen a proof using limits. But there's still this nagging question: why? For instance, why is there this plus sign in the product rule? I mean, really, with all those chiastic laws, the limit of a sum is the sum of the limits, limit of products to product of limits, you'd probably think the derivative of a product is the product of the derivatives. I mean, you'd think that if you differentiated a product, it'd just be the product of the derivatives. No, that's not how products work. What happens when you wiggle the terms in a product? We can explore this numerically. To play around with this, I've got a number A and another number B, and I'm multiplying them together to get some new number, A times B. Now initially I've set A equals 2 and B equals 3, so A times B is equal to 6, but now I can wiggle the terms and see how that affects the output. So what if I take A and move it from 2 to 2.1? Well, that affects the output. The output is now 6.3. Conversely, what if I move that back down and I move B from 3 to 3.1? Well, that makes the output from 6 to now 6.2. The deal here is that wiggling the input affects the output by a magnitude that's related to the size of the other number, right? When I went from 2 to 2.1, the output was affected by about 3 times as much, the 3. When I moved the 3 from 3 to 3.1, the output was affected by about 2 times as much. And these effects add together. What if I simultaneously move A from 2 to 2.1 and move B from 3 to 3.1? Then the output is 6.51, which is close to 6.5, which is what you'd guess the answer would be if you just add together these effects. We can see the same thing geometrically. Geometrically, the product is really measuring an area. So let me start with a rectangle of base f of x and height g of x. The product of f of x and g of x is then the area of this rectangle. Now, I want to know how this area is affected when I wiggle from x to, say, x plus h. So let's suppose that I do that. Let's suppose that I slightly change the size of the rectangle so that now the base isn't f of x anymore, it's f of x plus h, and the height isn't g of x anymore, it's g of x plus h. Now how does the area change when the input goes from x to x plus h? Well, that's exactly just computing this area in this L-shaped region here. I can do that approximately. I actually know how much the base changes approximately by using the derivative, right? What's this length here approximately? Well, the derivative of f at x times the input change is an approximation to how much the output changes when I go from x to x plus h. So this distance is approximately f prime of x times h. Same deal over here. When the input goes from x to x plus h, the output is changed by approximately the derivative times the input change. So this length here is about g prime of x times h. Now I'm trying to compute the area of this L-shaped region to figure out how the area, the product, changes when I go from x to x plus h. Let me cut this L-shaped region up into 3 pieces. This corner piece is pretty small, so I'm going to end up disregarding that corner piece. But let's just look at these 2 big pieces here. This piece here is a rectangle, and what's its area? Well, its base is f of x, and its height is g prime of x times h. So the area of this piece is f of x times g prime of x times h. What's the area of this rectangle over here? Well, its base is f prime of x times h, and its height is g of x. So the area of this piece is f prime of x, g of x times h. Now I want to know, how did the area change when I went from x to x plus h? Well, that's pretty close to just the sum of these 2 rectangles. So the change in area is about f of x times g prime of x times h plus f prime of x times g of x times h. The derivative is the ratio of output change, which is about this, to input change, which in this case is h. I went from x to x plus h. So now I can cancel these h's, and what I'm left with is f of x times g prime of x plus f prime x times g of x. That's the product rule. That's the change in the area of this rectangle when I went from x to x plus h, divided by how much I changed the input, h. The power rule isn't something that we just made up. It's not some sort of sinister calculus plot designed to turn your mathematical dreams into nightmares. This rule, the product rule, arises for understandable reasons. If you wiggle one of the terms in a product, the effect on the product has to do with the size of the other term. You add together these two effects, and then you have some idea as to how the product changes based on how the terms change. This is more than just a rule to memorize. It's more than just an algorithm to apply. The product rule is telling you something deep about how a product is affected when its terms are changed.